All right, in this explainer, we're going to break down one of the most fundamental tools in data science and AI. It's called regression. It's all about finding patterns and figuring out what might happen next. So let's dive right in.
So let's start with a big question, one that sounds like it's straight out of a sci-fi movie, right? Can a machine, an algorithm, actually look at what's happening now and tell us what's going to happen in the future?
Well, the answer is kinda. It can't magically see the future, but what it can do is make an incredibly educated guess by finding patterns in what's already happened. And one of the most important, a real cornerstone technique for doing this, is called regression.
At its heart, this whole thing is about solving what we call the prediction problem. How can we use the information we already have to make a really smart forecast about something we don't know yet?
Now, it might sound complicated, but the basic idea is actually super simple. Prediction is really just about finding a relationship between things. Once you understand how they're connected, you can use one to tell you something about the other.
Okay, let's make this really simple with an example we can all get. Just think about it. We all kind of know that as kids get older, they generally get taller. So, could we use a child's age to predict their height?
To answer a question like that, we have to find the pattern in the data. And honestly, the best way to see a pattern is often just to, look at it.
So let's actually plot it out. On this chart, every single dot you see represents one child. How far it is to the right tells us their age, and how high up it is tells us their height. This kind of visual is called a scatter plot, and it is an absolutely fantastic way to see relationships.
So take a look, and I mean really look. Forget all the math for a second. Just use your eyes. Do you see a general trend here? A direction that the dots seem to be heading?
Yeah, you probably spotted it right away. The dots aren't just a random cloud. They seem to form a rough line that goes up and to the right. In the world of statistics, we call this a positive correlation. It's the visual proof of what we already thought. As one thing, age, goes up, the other thing, height, also tends to go up. Okay, so here's where things get really cool. How do we take that rough visual pattern and turn it into a tool we can actually use for prediction? This is exactly where regression comes in.
Specifically, we're talking about something called linear regression. It's a fancy term for a pretty simple idea. It's a method for finding the single best straight line that slices right through all our data points and best describes their relationship.
So this is the key. Think about it. Out of all the trillions of possible lines you could draw through that cloud of dots, regression finds the one line that is, on average, the closest it can possibly be to every single dot at the same time. It's like the ultimate compromise.
So how on earth does it find that perfect line? Well, the most common way is something called the least squares method. Basically, the computer tries a line, and for every dot, it measures the vertical distance to that line. That's the error. Then it squares all those distances to make them positive. And finally, it fiddles with the line, tilting it, moving it up and down, until it finds the one single position where the sum of all those squared errors is as tiny as it can possibly be.
And this is where it becomes a prediction machine. That best fit line can be described by that simple equation you probably remember from school. Once we have that equation, we're golden. We can just plug in a new age for x, do the math, and it will spit out a predicted height for y.
But how do we know if our line is any good? I mean, is it an A+ fit or more of a C-? For that, we use a score called R². Just think of it like a grade from 0 to 1 that tells you how well the line actually represents the data. A score near 1 is great. A score near 0 means, not so much.
Okay, but before we get too excited and start predicting everything, we have to talk about a huge, massive, absolutely crucial warning that comes with this kind of analysis. You've probably heard this phrase before, and believe me, in the world of data, it is the absolute golden rule. Just because two things move together, it does not mean one causes the other. So a regression line might show you something really weird, like when ice cream sales go up, drowning incidents also go up. They're totally correlated, but does that mean eating a scoop of ice cream causes drowning? No, of course not. There's a hidden third factor, hot summer weather, that causes both more people to buy ice cream and more people to go swimming. This is called a confounding variable, and it's a trap you always have to look out for.
Here's a perfect modern example. You might notice two things happening at once on your phone. It starts hanging, and the camera app won't open. Those two things are correlated. They happen together. But the hanging doesn't cause the camera to fail.
The real cause, the hidden factor, is that your phone's memory is totally maxed out, and that one problem is causing both symptoms.
And there are a few other limitations you've got to keep in mind. Linear regression assumes the pattern is a straight line, but life isn't always linear. Also, it gives us a good approximation, an educated guess, but it's never a guarantee. And this is a big one. It's really only reliable inside the range of the data you use to build it. Our model that predicts a kid's height is going to be totally useless for predicting the height of a 45-year-old.
So, okay, with all those warnings in mind, where does this powerful but, imperfect tool actually show up in the real world? Well, the short answer is pretty much everywhere.
I mean, in finance, people are using it to try and forecast stock prices. In sales, businesses use it to predict how much they'll sell next month. Scientists use it all the time to model what's happening in their experiments. Even logistics companies use it to analyze traffic patterns and predict how long your delivery will take. Basically, if you're asking how much or how many, regression is probably working behind the scenes.
So, when you boil it all down, regression takes all this messy, chaotic data and gives us a clear model for making predictions. Now, it's not a crystal ball, not by a long shot, but it's an incredibly powerful way of finding the signal in all that noise. And that leaves us with a really big question, right? As we start to rely on these predictions more and more, how do we use this power responsibly?